What if everything you thought you knew about time was only half the story? Picture standing at the edge of a moment, watching the past and future swirl together like threads in a tapestry, each second not just a point on a line, but a doorway waiting to be opened. Time travel isn't just the stuff of blockbuster movies or science fiction novels. It's a mystery that has haunted scientists, philosophers, and dreamers for centuries, teasing us with possibilities that defy the very fabric of reality. Think about the grandfather paradox, where going back in time to change one small event could unravel your own existence, or the chilling idea of a future where time tourists wander through history like spectators in a museum. These aren't just wild fantasies, they're puzzles that some of the brightest minds in physics are racing to solve. Today, we're diving into 30 theories that could finally crack the code of time travel, ideas so bold they blur the line between science and imagination. Some of them stretch the laws of physics to their breaking point, while others suggest that time might not even flow the way we think it does. Could wormholes act as cosmic shortcuts through the ages? Might quantum mechanics hold the key to slipping between moments like a ghost? And what if the universe itself is built with layers of time, stacked like pages in a book, waiting for us to learn how to turn them? The answers might be closer than we think, hidden in equations and experiments happening right now in labs around the world. This isn't just about the how, it's about the why. What drives us to chase such an impossible dream? Maybe it's the longing to fix mistakes, to see history with our own eyes, or to glimpse the destiny of humanity. Or perhaps it's something deeper, a primal curiosity about the nature of existence itself. Whatever the reason, one thing's certain: the journey to understand time travel forces us to question everything we take for granted. So buckle up. By the end of this exploration, you might never look at a clock the same way again. The idea that time isn't fixed, that it can stretch and bend like taffy, comes straight from Einstein's groundbreaking theory of special relativity. Picture this: you're on a spaceship hurtling through the cosmos at nearly the speed of light. To everyone back on Earth, your clock would tick slower than theirs, meaning you'd age less while centuries pass for them. It sounds like science fiction, but this phenomenon, called time dilation, is very real. In fact, scientists have tested it with ultra-precise atomic clocks. When they placed one on a high-speed airplane and kept another on the ground, the airborne clock ran slightly slower, just as Einstein predicted. This isn't just a quirk of physics, it's a one-way ticket to the future. Imagine an astronaut spending a year orbiting Earth at incredible speeds. They'd return to find their twin sibling older than them, having experienced time at a different rate. The faster you go, the more extreme the effect becomes. At 99% the speed of light, a single day for you could mean years, or even decades for everyone else. But here's the catch: while special relativity lets you leap forward, it doesn't offer a path back. There's no rewinding the clock, no revisiting yesterday. What makes this even stranger is that time dilation isn't just about speed. Gravity warps time too. Einstein later showed that a clock at the top of a mountain ticks faster than one at sea level because Earth's pull is weaker higher up. So if you wanted to time travel to the future, you'd need extreme speed, crushing gravity, or both. It's as if the universe left us a loophole, one that turns the far future into a destination rather than a distant dream. The only problem: we'd need technology far beyond today's rockets to reach those mind-bending speeds. Until then, Einstein's theory remains both a tantalizing possibility and a reminder of how much we still don't understand about time itself. If Einstein's special relativity showed us how speed could bend time, his general theory of relativity takes things even further, revealing that gravity itself twists the fabric of reality. Picture spacetime not as a rigid stage but as a stretchy trampoline, sagging under the weight of massive objects like stars and planets. The heavier the object, the deeper the dent it creates, and the slower time ticks for anyone caught in that gravitational well. This isn't just theoretical. GPS satellites orbiting Earth have to account for this effect. Their clocks run slightly faster than those on the ground because they're farther from Earth's gravitational pull. Without these adjustments, your phone's navigation would be off by miles within minutes. Now imagine standing near the edge of a black hole, where gravity is so intense that not even light can escape. Here, time doesn't just slow down, it grinds to a near halt relative to the rest of the universe. The film Interstellar played with this idea when its crew visited a planet orbiting Gargantua, a supermassive black hole. For every hour they spent on that world's surface, 7 years passed back on Earth. While the movie took some creative liberties, the science behind it is shockingly real. Black holes are nature's ultimate time machines, stretching seconds into centuries for anyone brave enough to venture close. But here's the twist: gravitational time dilation isn't just about extreme cosmic monsters. Even Earth's modest gravity creates tiny time warps. If you've ever worked in a skyscraper, you've lived slightly faster than someone in the basement by about a few billionths of a second per year. It's a whisper of an effect, but it proves the universe operates by rules far stranger than our everyday experience suggests. And if we ever harness the power of a black hole's gravity, we might not just peer into the future, we could step into it. The catch: surviving the trip would require technology that doesn't exist yet. Until then, black holes remain both a tantalizing mystery and a reminder of how much we still have to learn about the warp and weft of time itself. But what if bending time wasn't just about speed or gravity? What if we could take a shortcut through the very fabric of spacetime? Enter wormholes, hypothetical tunnels that could connect two distant points in the universe or even different moments in time. Picture folding a sheet of paper so two dots touch. That's the basic idea. In theory, a wormhole would act like a cosmic subway, letting you step in one end and emerge light years away or centuries apart in the blink of an eye. The concept traces back to 1935, when physicists Albert Einstein and Nathan Rosen proposed the Einstein-Rosen bridge, a mathematical solution to Einstein's equations that suggested these tunnels might exist. But here's the problem: natural wormholes, if they exist at all, would likely be microscopic, unstable, and collapse instantly under their own gravity. To make one usable for time travel, you'd need something called exotic matter, a hypothetical substance with negative energy that could prop the wormhole open like scaffolding. Think of it as trying to hold open a collapsing tunnel with anti-gravity. Even if we could stabilize a wormhole, the paradoxes get dizzying. Open a wormhole to the past, and you might create a feedback loop where cause and effect unravel. Drop a clock into one end, and it could emerge before you threw it in. Some physicists speculate that quantum effects might prevent these paradoxes, like nature's own no entry sign for time tourists, but no one knows for sure. The wildest part: wormholes might already be all around us, just too small to see. Quantum foam, the frothy turbulence of spacetime at the tiniest scales, could be peppered with microscopic wormholes popping in and out of existence. Harnessing them would require technology beyond our wildest dreams, but the possibility lingers. Perhaps one day we'll find the key to these cosmic passageways. Until then, wormholes remain one of spacetime's most tantalizing what-ifs, bridges to places we can imagine but not yet reach. While wormholes offer one hypothetical path through time, another mind-bending approach comes from physicist Frank Tipler, a device so massive it twists spacetime itself into knots. Picture a cylinder as dense as a neutron star, spinning at nearly the speed of light and stretching infinitely into space. This isn't just sci-fi. Tipler's calculations showed such a structure could warp reality enough to create closed time-like curves, essentially bending the timeline into a loop where the end circles back to the beginning. Here's how it would work. The cylinder's insane rotation would drag spacetime around it like honey stirred by a spoon, creating a whirlpool effect. If you orbited this cosmic spindle in just the right path, you could find yourself on a trajectory where your future leads backward into your own past. It's like running laps on a racetrack where each loop takes you further into yesterday. The implications are dizzying. Meet your younger self, witness historical events firsthand, or even create paradoxes where cause and effect spiral endlessly. But there's a catch, or rather several. First, Tipler's cylinder would need to be infinitely long. Not improbably long, not astronomically long, but mathematically infinite, a requirement that's impossible in our finite universe. Second, the material required to build it would need to be tens of thousands of times denser than anything we've ever observed, defying known physics. Even if we somehow cobbled together a neutron star's worth of matter, keeping it perfectly aligned as it spins at relativistic speeds would be like balancing a skyscraper on a fingertip during an earthquake. And then there's the energy problem. Powering such a monstrosity would demand more resources than humanity has ever harnessed, like trying to fuel a bonfire with a single match. Yet despite these impossible hurdles, Tipler's idea remains fascinating because it proves something profound. The equations of general relativity don't forbid time loops. They're baked into the math, waiting for someone or something to unlock them. For now, the Tipler cylinder stands as a tantalizing what if, a reminder that the universe's rulebook might allow time travel even if our toolbox falls short. Perhaps the most haunting question isn't whether we could build such a machine, but what would happen if someone else already did. Hidden somewhere in the cosmos, could there be ancient, spinning relics left by civilizations far older than our silent time machines, whispering secrets across the ages? What if the universe itself contains hidden threads capable of stitching together moments across time? Cosmic strings, hypothetical defects in spacetime left over from the birth of the universe, might be the ultimate time-weaving tools. These filaments, thinner than an atom but stretching across billions of light years, are thought to carry immense density, warping spacetime around them like a needle pulling tight the fabric of reality. If they exist, two such strings moving in parallel at near light speed could theoretically twist spacetime into a closed loop, a time machine straight out of mythology. The math behind this is as elegant as it is bizarre. Picture two cosmic strings racing past each other like celestial scissors. The space between them would become so distorted that traveling around the pair could transport you to your own past. It's like walking in a spiral staircase where each rotation brings you back to an earlier step. Physicist Richard Gott, who pioneered this idea in the 1990s, showed that such a configuration wouldn't just bend time. It would fold it into a pretzel, allowing for journeys to moments already gone. But here's the catch: cosmic strings remain purely theoretical. No telescope has ever spotted one, though astronomers have searched for their faint gravitational signatures. Even if they do exist, harnessing them would require precision beyond our current reach. You'd need to maneuver unimaginably massive objects at relativistic speeds without snapping the strings, like trying to lasso two speeding freight trains with spider silk. And the energy required, it would dwarf the output of entire galaxies. Yet the allure of cosmic strings isn't just about practicality. They hint at a deeper truth: the universe might be threaded with invisible highways through time. Some theories suggest these strings could have formed microscopic loops during the Big Bang, tiny time machines scattered like confetti across the cosmos. If so, the key to time travel might not be building a machine at all, but finding one that's been hidden in plain sight since the dawn of existence. Until then, cosmic strings remain a breathtaking what if, whispering that the universe's greatest secrets might be written in threads we've yet to unravel. Quantum mechanics flips our everyday experience of time on its head. While we perceive time as an arrow flying relentlessly forward, the microscopic world plays by different rules, where particles can act as if time runs backward just as easily as forward. This eerie symmetry lies at the heart of one of quantum theory's most profound mysteries. Imagine watching a film of two electrons colliding and scattering apart. If you replayed that film in reverse, the equations governing their behavior would look identical. The physics works perfectly whether time flows forward or backward, as if the universe at its smallest scales doesn't care which way the clock ticks. This idea captivated physicists like John Wheeler and Richard Feynman, who proposed a radical explanation in the 1940s called the absorber theory. Picture a lone electron jiggling in space, emitting ripples of energy into the future. Normally, we'd expect those ripples to fade into emptiness. But Wheeler and Feynman suggested something astonishing. What if those ripples are eventually absorbed by matter in the far future, and that absorption sends an echo backward through time, perfectly cancelling out the original emission? It's like shouting into a canyon and having the echo return before your voice even leaves your lips. The result, time symmetry so perfect, the electron's behavior makes equal sense whether you view it from past to future or future to past. Critics argue this interpretation stretches intuition to the breaking point. After all, we never see teacups reassemble from shattered fragments or smoke funneling back into a cigarette. But quantum experiments consistently show particles behaving in ways that ignore our everyday sense of time's flow. In labs, quantum systems can exhibit retrocausality, where measurements made in the present seem to influence events that already happened. It's as if the universe keeps its options open until the last possible moment, refusing to commit to a single timeline. The implications for time travel are staggering. If quantum processes truly don't distinguish between past and future, could we exploit that ambiguity to send information or even particles backward through time? Some researchers speculate that entangled particles, those spooky twins of quantum physics, might hold the key, manipulate one in the present, and its partner could respond as if the effect preceded the cause, like a ripple moving upstream against time's current. Yet for all its elegance, quantum time symmetry collides with a harsh reality. Our macroscopic world stubbornly obeys the arrow of time. Heat flows from hot to cold, eggs don't unscramble, and memories only accumulate in one direction. Bridging this gap between quantum whimsy and classical reality remains one of physics' greatest challenges. Until we solve it, the quantum realm offers a tantalizing glimpse of time's fluidity, a reminder that the universe's rulebook might be far stranger than we've dared to dream. What if every decision you've ever made spawned an entirely new universe? The many worlds interpretation of quantum mechanics suggests just that, an infinite web of parallel timelines branching from every possible outcome. This mind-bending theory might hold the key to time travel without paradoxes. Picture stepping into a time machine and journeying to prevent a historical tragedy. Instead of altering your original timeline, you'd simply split off into a new reality where that event never occurred, while the original timeline continues untouched. Your grandmother still meets your grandfather in one universe, even as you shake hands with her in another. The roots of this idea trace back to physicist Hugh Everett in the 1950s. He proposed that quantum events don't collapse into single outcomes but unfold across countless realities. Flip a quantum coin and both heads and tails happen, just in separate worlds. Apply this to time travel, and suddenly the grandfather paradox evaporates. There's no need to worry about erasing your own existence when every action spawns fresh timelines like new chapters in an endless book. Some physicists argue this could explain why we've never met time tourists from the future. They might be here, just in parallel dimensions we can't perceive. The Large Hadron Collider has even searched for evidence of gravity leaking from adjacent universes, though conclusive proof remains elusive. Meanwhile, quantum experiments keep revealing particles that seem to remember multiple histories simultaneously, as if reality itself hesitates to choose just one path. But the many worlds approach raises profound questions. If alternate timelines constantly branch, does every possible version of history exist somewhere? Could there be realities where dinosaurs never went extinct, or where ancient Rome developed steam engines? The implications stretch beyond physics into philosophy. What does it mean for free will if every choice spawns new worlds? And if we could hop between timelines, how would we ever find our way back home? One tantalizing possibility involves quantum entanglement, those mysterious particle connections Einstein called spooky action at a distance. Some theorists suggest entangled particles might act as anchors between worlds, their synchronized behavior hinting at hidden pathways through the multiverse. Imagine a future where time machines don't move through years but sideways across realities, navigating the cosmic tree of alternate histories like climbers choosing branches. The many worlds theory transforms time travel from a paradox into a kaleidoscope, one where every journey creates ripples in realities we may never see. It suggests our universe is far wilder than we imagined, with infinite versions of ourselves making different choices in worlds just beyond our reach. Whether these parallel timelines truly exist remains one of physics' greatest mysteries, but the idea alone reshapes what time travel could mean, not as rewriting history, but as discovering how much history has left to write. Einstein's equations hold a strange gift buried in their mathematics paths that loop back on themselves like cosmic Möbius strips, where the future inevitably circles around to meet the past. These are closed time-like curves, or CTCs, theoretical pathways through spacetime that could allow a traveler to return to their own history without ever changing direction. Picture walking forward along a winding mountain trail only to realize you've ended up exactly where you started, but in an earlier time. It's not science fiction, it's a genuine prediction of general relativity, where the fabric of reality twists so tightly that cause and effect stitch themselves into a knot. The most fascinating part, these loops might sidestep the paradoxes that haunt other time travel theories. Enter the Novikov self-consistency principle, proposed by Russian physicist Igor Novikov in the 1980s. It suggests the universe has a built-in editing feature. Any action taken within a closed time-like curve would automatically adjust to avoid contradictions. Say you try to go back and prevent your parents from meeting. Novikov's principle insists the universe would conspire to make you fail. Maybe your time machine misfires, or a sudden storm forces them indoors where they're destined to cross paths anyway. The timeline self-corrects like a river flowing around a rock, ensuring events unfold exactly as they always have. This idea gained traction when physicist Kip Thorne applied it to wormholes, showing how quantum effects might enforce consistency. Imagine dropping a billiard ball into a time-looping wormhole so it emerges in the past and collides with its younger self, knocking it off course. Novikov's principle dictates the ball's path would adjust subtly, angles of impact shifting, speeds altering, so the collision always plays out in a way that leaves the original timeline intact. It's as if the universe has a fail-safe against paradoxes, tweaking probabilities behind the scenes to maintain logical harmony. Critics argue this feels suspiciously like destiny wearing a lab coat. If every attempt to change the past is doomed to reinforce it, does free will evaporate inside a closed time-like curve? Some interpretations suggest free choice remains, but the range of possible actions narrows to only those consistent with history. You'd retain the illusion of autonomy while unknowingly playing your part in a predetermined script. The implications ripple beyond physics. If CTCs exist, they might explain why we haven't encountered time tourists. Perhaps the universe naturally restricts access to prevent paradoxes. Or maybe, as some theorists speculate, we're already living inside a self-consistent loop, where every innovation, every discovery was subtly influenced by visitors from the future ensuring their own existence. It's a dizzying thought. The key to time travel might not be breaking the rules of causality, but discovering how tightly those rules bind us all. Imagine a spacecraft not constrained by the speed of light, a vessel that doesn't move through space so much as it moves space itself. This is the Alcubierre warp drive, a concept so audacious it bends the rules of relativity without breaking them. Proposed by physicist Miguel Alcubierre in 1994, the idea hinges on a clever loophole. While nothing can travel faster than light within spacetime, spacetime itself has no speed limit. Picture a surfer riding a wave, but instead of water, the wave is the fabric of the universe. The ship sits in a warp bubble, with spacetime compressing in front of it and expanding behind, hurling the craft forward while it remains motionless inside. Relative to the outside universe, you could arrive at your destination faster than light. And astonishingly, before you even left, here's where it gets wild. This isn't just faster than light travel, it's a backdoor to time travel. Einstein's equations show that if you could outpace light, you'd also outpace causality, effectively reaching a point in spacetime where your arrival precedes your departure. A round trip under warp drive could deposit you back home before you launched, like mailing a letter that arrives yesterday. The Alcubierre metric even accounts for time dilation effects, with clocks inside the bubble ticking differently from those outside. It's as if the drive doesn't just cheat distance, it cheats time itself, but there's a cosmic catch. To create this spacetime contorting bubble, you'd need exotic matter, a hypothetical substance with negative energy density. Unlike anything in our everyday experience, this matter would repel gravity rather than attract it, acting like cosmic anti-gravity to pry open the warp bubble. The problem: no one's ever found definitive proof such matter exists. Quantum mechanics hints at fleeting negative energy in phenomena like the Casimir effect, where vacuum fluctuations create minuscule attractive forces between metal plates. But scaling this up to power a starship would require harvesting amounts of negative energy comparable to the mass of Jupiter. Even if we cracked the exotic matter puzzle, other hurdles loom. The warp bubble's edges would concentrate staggering amounts of energy, potentially vaporizing anything at the destination upon arrival. Some calculations suggest the drive might also emit lethal radiation or create unpredictable gravitational waves. And then there's the control problem: steering a warp bubble without tearing apart spacetime in your wake. Yet the Alcubierre drive captivates because it's not pure fantasy. NASA Eagleworks Lab has conducted preliminary experiments with warp field interferometers, searching for microscopic spacetime distortions. While breakthroughs remain distant, the math persists, whispering that the universe might allow shortcuts after all. Perhaps one day, humanity will need the fabric of reality like dough, folding time and space to our will. Until then, the warp drive stands as both a beacon of possibility and a humbling reminder. The cosmos keeps its greatest secrets guarded by layers of physics we've only begun to peel. What if the key to manipulating time wasn't some colossal cosmic structure, but a tiny, shimmering crystal that ticks like a clock without ever winding down? Enter time crystals, one of the most bizarre and groundbreaking discoveries in modern physics. Unlike ordinary crystals, which arrange their atoms in repeating patterns across space, time crystals exhibit structure that repeats in time. They oscillate between states indefinitely, like a perpetual motion machine at the atomic scale. First theorized by Nobel laureate Frank Wilczek in 2012, these exotic phases of matter defy one of science's most sacred principles, the law of energy conservation. They pulse, rotate, or flip states in a never-ending dance without absorbing or emitting energy, as if the universe handed them a free pass to ignore thermodynamics. The secret lies in what physicists call broken time symmetry. Picture pushing a child on a swing. Normally, the swing responds immediately to your push, moving in perfect sync with your efforts. But imagine if the swing only moved every second time you pushed, a rhythm out of step with the force applied. That's the essence of a time crystal, a system that settles into a repeating pattern with a different tempo than the energy driving it. This isn't just theoretical. Scientists have created time crystals in labs using chains of ions, supercooled atoms, and even diamond imperfections. In 2017, teams at Harvard and the University of Maryland made headlines by observing these strange structures in quantum systems, their atoms flipping spin states in a predictable, self-sustaining cycle millions of times before dissipating. What makes time crystals tantalizing for time travel research is their eerie resemblance to miniature time loops. Some theorists speculate they could serve as prototypes for understanding how larger systems might break free from time's arrow. Imagine a future where arrays of time crystals act as quantum clocks, synchronizing processes across distorted spacetime or even encoding information that resists entropy's erasure. There's even wild speculation that certain configurations might allow limited causality violation, where an effect subtly precedes its cause within the crystal's rhythmic framework. Of course, practical applications remain distant. Current time crystals exist only in carefully isolated quantum systems, frailer than a soap bubble and vanishing at the slightest disturbance. Scaling them up would require harnessing quantum coherence on unprecedented scales, a challenge akin to building a sandcastle that doesn't crumble under its own weight. Yet their very existence reshapes our understanding of time's malleability. If matter can lock into perpetual motion against the universe's thermodynamic tide, who's to say other, impossible temporal phenomena aren't waiting to be uncovered? Time crystals don't just tick, they whisper that time itself might be more fluid, more strange than we ever dared to dream. Black holes aren't just cosmic vacuum cleaners, they're nature's most extreme time machines, warping the fabric of reality to the breaking point. At the heart of this possibility lies the Kerr black hole, a spinning monstrosity so violent it twists spacetime into a vortex. Unlike stationary black holes, Kerr black holes drag the very fabric of the universe around them like water circling a drain, creating a region called the ergosphere where the laws of physics as we know them begin to unravel. Step inside this zone, and you're no longer in control of your own trajectory. Space itself is moving so fast that standing still becomes impossible. But here's where things get wild. If you could skim the edge of the ergosphere without being ripped apart, you might exploit this relativistic dragging to effectively travel through time. The math behind this is both beautiful and terrifying. A spinning black hole's rotation generates what's known as frame dragging, where spacetime is pulled so forcefully that it creates closed time-like curves, loops in time that could theoretically allow you to circle back to your own past. Picture a cosmic carousel spinning so fast that every revolution takes you further backward along the timeline. Some calculations suggest that by carefully navigating the ergosphere's chaotic currents, a spacecraft could hitch a ride on these twisted spacetime pathways, emerging in an earlier moment without ever exceeding the speed of light. It's like surfing a wave that rolls backward through time itself, but the risks are beyond apocalyptic. The tidal forces near a black hole's event horizon would stretch any object into spaghetti long before it reached the ergosphere. Radiation from the accretion disk, a swirling maelstrom of superheated gas, would vaporize anything not already torn apart by gravity. And even if you survived the approach, the ergosphere's chaotic physics might spit you out at random points in spacetime, or worse, trap you in an infinite loop, reliving the same moment for eternity. The unpredictability of black holes means there's no guarantee you'd exit when or where you intended. You might emerge billions of years in the past or find yourself in a parallel universe altogether. The unknowns are just as daunting as the dangers. Quantum effects near the singularity could rewrite the rules entirely, with phenomena like Hawking radiation or firewall paradoxes potentially destroying any would-be time traveler. Some theories even suggest that the universe might prevent such exploits entirely, with quantum mechanics conspiring to keep causality intact. After all, if time travel via black holes were possible, why haven't we encountered visitors from the future? Unless, of course, they're hiding in the ergosphere's shadow, or we're looking in the wrong places. Yet, despite these nightmarish hurdles, Kerr black holes remain a tantalizing theoretical playground. They prove that Einstein's equations allow for time loops under extreme conditions, even if nature erects cosmic keep-out signs around them. For now, black hole time travel remains the domain of supercomputers and chalkboard equations, a reminder that the universe's most profound secrets often lie just beyond the edge of oblivion. Quantum entanglement is often called spooky action at a distance. For a reason, two particles can become so deeply linked that measuring one instantly determines the state of the other, no matter how far apart they are. But what if this eerie connection isn't just bridging space, but time itself? Recent experiments have uncovered hints that entangled particles might defy our linear perception of cause and effect, behaving as if they're communicating across moments that haven't happened yet. Picture tossing a pair of quantum dice where one die lands before you've even thrown the other, yet somehow their outcomes always match. This perplexing phenomenon traces back to groundbreaking experiments by physicists like John Bell in the 1960s, whose work proved entanglement couldn't be explained by hidden variables or classical physics. But the real twist came decades later, when researchers like Anton Zeilinger began testing whether these quantum correlations could stretch across time as seamlessly as space. In one mind-bending experiment, scientists measured particles in an order that effectively forced the effect to occur before the cause. The results: the particles behaved as if the future were influencing the past, like ripples in a pond flowing backward to the pebble's splash. Some theorists propose this could hint at retrocausality, the idea that future events subtly shape the past. It's not quite time travel as Hollywood imagines it, but more like the universe playing a cosmic game of telephone between moments. Imagine a pair of entangled photons created in a lab today. If one is measured tomorrow, could its state somehow reach back to influence its partner yesterday? The mathematics suggests it's possible, though interpreting what that means divides physicists. Some argue it's just a quirk of quantum math with no real temporal consequences, while others see it as evidence that time's arrow might be softer than we think, able to bend or even fold under the right conditions. The implications ripple far beyond theory. If quantum entanglement truly links different points in time, it could revolutionize communication. Imagine sending encrypted messages not just across continents, but across centuries. A quantum time capsule where information is encoded in particles whose states are locked to future measurements. There's even wild speculation about exploiting entanglement to build a quantum beacon, a signal fired into the future by manipulating particles in the present. Yet the mysteries deepen when you consider the paradoxes. If future actions can influence past events, does that mean destiny is written in quantum code? Or does the universe simply keep its options open until the last possible moment, editing the timeline like a draft? While no one's claiming we'll build a time machine from entangled particles anytime soon, these experiments force us to confront a radical possibility. The threads connecting moments in time might already be woven into the fabric of reality, tiny, invisible strands waiting to be pulled. Stephen Hawking once placed a tongue-in-cheek bet against time travel, not because he thought it was impossible, but because the universe itself might forbid it. This idea became known as the chronology protection conjecture, a cosmic safeguard woven into the laws of physics to prevent paradoxes from unraveling reality. Picture time as a meticulous librarian stamping "return by" dates on every event to ensure cause and effect stay neatly shelved. Hawking argued that any attempt to travel backward would trigger catastrophic feedback loops, like a microphone screeching when placed too close to a speaker, until nature intervenes to shut the whole system down. The evidence for this cosmic censorship, Hawking pointed to the eerie absence of time tourists. If time travel were ever invented, he reasoned, why hadn't future historians flooded the present? His playful Party for Time Travelers experiment, where invitations were only publicly announced after the event, resulted in 0 guests. But the conjecture runs deeper than a clever thought experiment. Quantum mechanics suggests that vacuum fluctuations near a potential time loop would amplify uncontrollably, creating an energy surge powerful enough to collapse the pathway. It's as if spacetime has an immune system, attacking temporal paradoxes like infections before they can spread. Critics counter that Hawking's conjecture is less a law than a placeholder, a confession of ignorance dressed in equations. After all, general relativity permits closed time-like curves, and quantum theories like retrocausality flirt with backward influence. Some physicists propose that paradoxes might simply self-correct through mechanisms we don't yet understand. Think of a river encountering a boulder. The water doesn't stop flowing, it finds a new path around the obstacle. Similarly, the universe might resolve contradictions by spawning parallel timelines, as in the many worlds interpretation, or enforcing Novikov's self-consistency principle, where any time-traveling intervention was always part of history. The debate touches on one of physics' deepest divides. Does the universe prioritize mathematical elegance or narrative coherence? Hawking's conjecture leans toward the latter, implying nature has a storyteller's aversion to plot holes. Yet the mathematics of wormholes and warp drives stubbornly refuse to veto time travel outright. Until we uncover a unified theory weaving together quantum mechanics and gravity, chronology protection remains a tantalizing, maybe a cosmic safety net whose threads we're still learning to trace. For now, it stands as both a warning and an invitation. Perhaps time travel isn't impossible, just waiting for us to outsmart the universe's firewall. What if the universe holds particles so bizarre they're born breaking the ultimate speed limit? Tachyon's hypothetical particles that only exist traveling faster than light are one of physics' most provocative what-ifs. Unlike everything else in the known cosmos, these phantoms wouldn't slow down to light speed. They'd treat it as an unreachable minimum, zipping through space with impossible velocity. But here's the twist. Einstein's equations suggest that anything moving faster than light would experience time in reverse. Send a tachyon message across the galaxy, and it might arrive before you sent it, like a cosmic version of receiving a letter postmarked with yesterday's date. The math behind this is as elegant as it is unsettling. Special Relativity's famous equation, E equals mc squared, implies that as objects approach light speed, their energy skyrockets toward infinity. But for tachyons, the equation flips. The slower they go toward light speed, the more energy they'd require. At rest, they'd need infinite energy, meaning they could never stop moving. And if you tried to observe one, you'd confront a paradox straight out of a time travel thriller. Detecting a tachyon at one point in space might mean its emission hasn't happened yet in your frame of reference. It's as if the particle's entire existence is a glitch in causality's code. Scientists have hunted for tachyon signatures everywhere, from particle colliders to cosmic ray detectors. Some thought they'd glimpsed them in early experiments with neutrino speeds, but those results were later debunked as measurement errors. Quantum field theory even allows for tachyonic fields, states where particles briefly behave as if they have imaginary mass, though these are mathematical artifacts rather than genuine faster-than-light entities. Yet the tantalizing possibility remains. If tachyons exist, they'd be natural time capsules, carrying information from the future to the past without the need for wormholes or warp drives. But the universe seems to have safeguards. If tachyons could freely interact with ordinary matter, they'd open floodgates of paradox. Imagine a scientist receiving a tachyon-born warning of their own lab explosion, only to evacuate and prevent the disaster, negating the very message that saved them. This self-contradiction suggests why tachyons, if real, might be censored by nature. Perhaps they only interact weakly with our world or exist in hidden dimensions. The deeper intrigue lies in what tachyons reveal about spacetime's architecture. Their theoretical existence hints that light speed isn't just a barrier, it's a cosmic horizon separating two mirror-image realities. On one side, particles like us bound by causality's arrow, on the other, tachyons forever untethered from time's forward march. Exploring their physics forces us to ask, is the universe's rulebook more flexible than we imagined, or are tachyons nature's way of teasing us with possibilities just beyond reach, a no trespassing sign hung at the edge of physics itself? For now, tachyons remain ghosts in the equations, whispering of a backwards ticking clock we can't quite wind. But their legacy endures, challenging us to rethink the most fundamental question of all. In a universe where time can bend, could it also sometimes run in reverse? We think of dimensions as directions we can move through, left and right, forward and backward, up and down. But what if time isn't just a relentless current carrying us forward? What if it's a dimension we could navigate, just like space? This radical idea, hinted at in H.G. Wells' The Time Machine, suggests that time might be less like a river and more like a landscape, with peaks and valleys we could traverse if only we knew the path. Wells' fictional inventor didn't just stumble into time travel, he treated it as a journey through a dimension, building a machine that could climb or descend the slopes of time as easily as a car drives over hills. In reality, Einstein's theory of relativity already merges space and time into a single fabric called spacetime, where the fourth dimension isn't some abstract idea but a fundamental part of the universe's structure. The catch: while we move through space in any direction we choose, time seems to push us relentlessly forward at 1 second per second. But here's where it gets fascinating. Physicists have long debated whether this asymmetry is a fundamental law or just a limitation of our perception. After all, the equations of general relativity don't care which way time flows, they work just as well backward as forward. It's only when you add entropy, the inevitable decay of order into chaos, that time gains its arrow. Imagine a deck of cards, shuffle it, and it's easy to create disorder, but nearly impossible to return it to its original state by chance. That's entropy in action, the hidden force that makes time feel one way. Yet some theories suggest that if we could manipulate space-time on a grand enough scale, we might sidestep entropy's grip. Wormholes, for instance, could act as elevators between floors of time, connecting distant moments as directly as a hallway connects rooms. Or consider warp drives, which compress space-time ahead of a ship and expand it behind, effectively surfing the fourth dimension. Even gravity itself could be the key. Near a black hole's event horizon, time stretches like taffy, meaning a few hours there could equate to years elsewhere. The challenge isn't just technological, it's conceptual. We're three-dimensional creatures trying to envision movement through four. It's like explaining left and right to a stick figure living on paper. Without depth, the idea of up is incomprehensible. But if time truly is a dimension, then our current experience might be akin to floating down a river, oblivious that we could theoretically swim against the current. The question isn't whether time is a dimension, but whether we'll ever learn to climb its invisible axis, turning Wells' fiction into physics. Until then, the fourth dimension remains a frontier, taunting us with possibilities just beyond our grasp. One of the most mind-melting paradoxes in time travel isn't about changing history, it's about erasing origins entirely. The bootstrap paradox, also called the ontological paradox, creates objects or ideas that seemingly come from nowhere, trapped in an infinite loop of cause and effect with no beginning. Imagine a time traveler bringing Beethoven's Fifth Symphony back to the 18th century and handing it to the composer himself, who then publishes it as his own work. Centuries later, that same symphony is discovered by the time traveler, who takes it back to Beethoven, creating a perfect circle where the music was never actually composed by anyone. It's like a snake swallowing its own tail, a riddle without an answer. This isn't just a thought experiment, it strikes at the heart of free will and creativity. If a time traveler gives Shakespeare a complete copy of Hamlet, did the bard truly author it, or was he merely a scribe for a future he'd never experienced? The paradox forces us to ask whether ideas can exist independently of their creators, floating through time like ghosts waiting to be discovered. Some philosophers argue this implies a predetermined universe where every innovation, every masterpiece, might just be an echo from a future that already happened. Others suggest these loops reveal a universe that doesn't care about origins, only consistency. The bootstrap paradox gets even stranger when applied to objects. Picture a watchmaker who receives a broken timepiece from a mysterious stranger, repairs it, and keeps it for decades until he eventually becomes that stranger, traveling back to give his younger self the same watch. The watch was never manufactured, it just is, a relic with no factory, no original craftsman. Quantum physics even toys with similar ideas, where particles can exist in superpositional states until observed, as if they're waiting for causality to catch up. But the real horror of the bootstrap paradox isn't the missing origin, it's the emptiness at the center. If free will is an illusion, if every original thought is just a borrowed fragment from tomorrow, what does that mean for human agency? Are we authors of our destiny, or actors reciting lines from a script written by time itself? The paradox offers no answers, only a dizzying hall of mirrors where questions reflect back on themselves endlessly. Perhaps that's the ultimate lesson. Time travel doesn't just bend physics, it unravels the very notion of where things and even ideas begin. The predestination paradox is time's cruelest joke, a trap where every attempt to change history only locks it tighter into place. Imagine traveling back to stop a terrible accident, only to realize your very presence causes the catastrophe you hope to prevent. This isn't just a plot twist from a sci-fi thriller. It's a real philosophical nightmare baked into the math of time travel. The paradox gets its name from the chilling idea that some events might be predestined, their outcomes sealed no matter how hard we fight against them. Like a mouse in a treadmill, the time traveler runs and runs, only to find they've been powering the machine all along. Take the classic example of a scientist who builds a time machine to stop a fire that killed her parents as children. She rushes into the past, only to knock over a lantern in the frantic moment of her arrival, igniting the very blaze she meant to extinguish. Her failure wasn't due to bad luck, it was inevitable. The fire had to happen because it did happen, and her intervention was always part of that timeline's equation. The universe, in this view, isn't just indifferent to our free will, it's actively conspiring to cancel it out. This eerie symmetry shows up in physics too. Closed time-like curves, those theoretical loops in spacetime, demand self-consistency. Any action within them must align perfectly with what's already occurred, like a jigsaw piece fitting into a puzzle that was complete before you started. Try to scribble outside the lines, and reality itself might erase your pen strokes. Some interpretations of quantum mechanics even suggest that probability waves collapse in ways that preserve consistency across time, as if the universe is constantly editing itself to avoid plot holes. But the real horror of the predestination paradox isn't just the loss of agency, it's the existential vertigo it triggers. If your future is already written, are you making choices or just performing them? Could every decision you've ever made be the echo of a time traveler's meddling, a ripple from a future you haven't lived yet? The paradox forces us to confront whether time is a river we can swim against or a Mobius strip with only one surface. Perhaps the only escape is to stop fighting the loop, to realize that in a universe where time folds back on itself, the act of trying to break free might be the very thing that binds you. After all, if destiny is inevitable, maybe the real freedom lies in choosing how you meet it. What if time isn't fundamental at all, but more like an illusion, a shadow cast by something far deeper and stranger? The holographic principle, a radical idea born from black hole physics. suggests our three-dimensional reality might be a projection of information encoded on a two-dimensional surface, like a cosmic DVD encoding an entire movie. But here's the twist: if space is an illusion, why not time too? Some physicists speculate that what we experience as the steady flow of seconds could be nothing more than a side effect of how this underlying information vibrates and interacts. A cosmic sleight of hand tricking us into believing in past, present, and future. The roots of this idea stretch back to the 1990s, when physicists Gerard T. Hooft and Leonard Susskind realized that the information swallowed by a black hole couldn't truly vanish. Instead, it seemed to be smeared across the event horizon, the point of no return, like a scrambled message written in vanishing ink. This led to a breathtaking possibility. Maybe everything inside the black hole, every particle, every force, was just a translation of that surface data. Apply this to the entire universe, and you get the holographic principle. Our 3D reality might be a pixelated mirage emerging from a flat, timeless substrate. Now imagine time in this framework. If the universe is a hologram, then the ticking clock we're enslaved to could be like the motion in a movie, an emergent property of frames flickering in sequence with no real movement at all. Quantum experiments already hint at this strangeness. Entangled particles seem to respond to each other instantly, as if distance, and by extension, time, is just a superficial layer over a deeper connectedness. It's like watching a play and realizing the actor's gestures are puppeteered by strings you can't see, moving to rhythms outside the stage's illusion. The implications are staggering. If time isn't fundamental, then time travel might not mean bending the fourth dimension. It could mean hacking the code beneath reality itself. Picture a programmer editing a video game source code to rewind a character's actions. In a holographic universe, altering the source information could rewrite history without paradoxes, because cause and effect would just be surface-level patterns. But here's the catch: we're like fish trying to perceive the water we swim in. Our brains evolved to navigate a world of cause and effect, making it nearly impossible to intuit a timeless reality. Even the language we use, words like before and after, reinforces the illusion. Yet math doesn't lie. Equations describing holographic universes often erase time entirely, replacing it with abstract relationships between data points. It's as if the universe is a symphony written in a language where when doesn't exist, only how. So where does this leave time travel? If the holographic principle holds, traversing years might not require wormholes or warp drives, but something far more profound: learning to read and rewrite the cosmic projection itself. The past and future could be frozen together in the hologram's code, waiting to be accessed like chapters in a book we've only just begun to decipher. Until then, the holographic universe taunts us with its most unsettling lesson. The flow of time might be the grandest illusion of all. If black holes are the universe's ultimate shredders dragging matter into oblivion beyond the event horizon, then white holes are their bizarre cosmic opposites, fountains of existence spraying out light and matter like a celestial fire hose. Imagine a black hole playing in reverse, where instead of swallowing everything that comes near, it violently expels it, refusing to let anything in. First theorized as a mathematical curiosity in Einstein's equations, white holes represent a tantalizing possibility that somewhere in the universe, time might be running backward on a cosmic scale. The symmetry is uncanny. While a black hole's gravity is so strong that not even light can escape, a white hole would have such repulsive force that nothing could enter, not even a single photon. Drop a rock toward one, and it would hit an invisible barrier, bouncing away as if the universe itself had hung a "Do Not Disturb" sign. Some physicists speculate that white holes could be the other end of black holes, a hypothetical tunnel through spacetime where what goes in one end bursts out the other. Picture a drain pipe where water pours down one side but gushes upward on the opposite end, defying logic. But here's where it gets even stranger. If white holes exist, they might not just be spatial anomalies. They could be black holes flipped inside out in time. A black hole forever pulls matter toward its singularity, compressing it into an infinitely dense point. A white hole, by contrast, might be that same singularity decompressing, spewing everything back out in a big bang-like explosion. It's as if the universe hit rewind on a black hole's life cycle, turning collapse into eruption. This idea aligns with physicist Lee Smollen's wild suggestion that every black hole in our universe could birth a new one inside it, a white hole, Big Bang, creating an entirely separate cosmos where time flows differently. The problem: white holes violate the second law of thermodynamics, which states that entropy, or disorder, always increases. A white hole spontaneously generating order from nothing would be like a shattered vase reassembling itself mid-air. Yet quantum mechanics offers a loophole. Some models suggest white holes could form momentarily during the collapse of certain types of black holes, flickering into existence for fractions of a second before vanishing in a burst of Hawking radiation. Others propose that the Big Bang itself might have been a white hole event, the ultimate cosmic rebirth. The most mind-bending implication: if white holes are truly time-reversed black holes, then witnessing one would be like watching a movie backward. Light rays near a white hole would bend away from it, creating bizarre visual effects. An object approaching might appear to slow, stop, and then accelerate backward as if pulled by invisible hands. Time itself could flow in reverse in its vicinity, turning cause and effect into a surreal puzzle. For now, white holes remain mathematical phantoms. No telescope has ever spotted one. But their possibility lingers, challenging us to rethink the most fundamental question of all. Is time's arrow truly fixed, or could the universe harbor pockets where it spins in reverse? Until we find proof, white holes stand as both a tantalizing "what if" and a humbling reminder that the cosmos might still hold tricks far stranger than we've dared to imagine. What if time travel doesn't require machines or black holes, just the untapped power of the human mind? Some of the most radical theories in physics and psychology suggest consciousness itself might be the ultimate vehicle for traversing time. Think about those eerie moments when déjà vu grips you, or a dream seems to predict an event before it happens. These fleeting experiences hint at a mind unshackled from linear time, brushing against moments it shouldn't logically access. Near-death experiences offer some of the most compelling, if controversial, glimpses into this possibility. Survivors often report vivid journeys through tunnels of light, encounters with departed loved ones, or even panoramic reviews of their entire lives, events that feel hyper-real and timeless. But some go further, claiming to witness future events that later unfold exactly as seen. In one well-documented case, a cardiac arrest patient accurately described a nurse's shoes from an overhead perspective during his resuscitation, a vantage point impossible for his unconscious body. Even stranger, he recalled glimpsing a future conversation between his doctor and wife, which played out word for word days later. Skeptics dismiss these accounts as hallucinations, yet the precision of some details challenges easy explanation. Psychedelics like DMT or psilocybin mushrooms amplify these mysteries. Users frequently describe losing all sense of time, visiting landscapes that feel simultaneously ancient and futuristic, or merging with entities who impart knowledge about past and future events. Indigenous cultures have long used these substances for vision quests, seeking guidance from ancestors or foresight about coming challenges. Modern neuroscience reveals that psychedelics temporarily quiet the brain's default mode network, the system responsible for our linear sense of time, as if lifting a veil to reveal time's fluid undercurrent. Theoretical frameworks struggle to explain these phenomena, but some physicists speculate about quantum consciousness. In this view, our brains might interact with spacetime at a fundamental level, with microtubules in neurons acting as quantum antennas. If consciousness extends beyond the brain akin to a radio tuning into signals, then time's arrow could be more permeable than we think. It's a stretch for mainstream science, but even skeptics admit the hard problem of consciousness remains unsolved. Perhaps the most haunting question isn't whether the mind can travel through time, but whether it ever truly stays put. If consciousness isn't bound by the same rules as matter, the past and future might not be distant lands, just frequencies we haven't learned to tune into yet. Until we crack the code, these fleeting glimpses remain both tantalizing clues and reminders of how little we understand about time's grip on the mind. What if your brain isn't just processing time but subtly bending it? The Orch-or theory, proposed by Nobel Prize-winning physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests consciousness arises from quantum processes deep within our neurons, and these tiny quantum events might not play by time's normal rules. Picture trillions of minuscule quantum computations flickering inside structures called microtubules, the skeletal fibers of your brain cells. These aren't just biological wires. Penrose and Hameroff propose they're the universe's smallest theaters, where quantum superposition and collapse generate moments of awareness. And if quantum states can exist outside classical time, as experiments suggest, then consciousness itself might flicker across timelines like a candle flame dancing between drafts. The implications for time perception are staggering. Quantum particles famously exhibit spooky behaviors, entanglement linking them across space, retrocausality suggesting influences can flow backward. If our brains harness these effects even fleetingly, it could explain déjà vu's eerie familiarity or precognitive dreams that seemingly preview future events. Imagine your neurons as quantum radios, occasionally tuning into signals not just from the present, but from adjacent moments in time. Orch-or speculates that during near-death experiences, when the brain's electrical activity flatlines, these quantum states might persist briefly, allowing consciousness to float free of linear time entirely. Patients who report seeing future events during cardiac arrest could be glimpsing a reality where quantum information isn't bound by chronological order. Critics argue the brain is too warm and chaotic for delicate quantum effects. Yet Penrose counters that microtubules might exploit biological superconductivity or topological qubits, shielding quantum information long enough to influence neural processes. Recent experiments on photosynthesis show quantum coherence in warm, messy biological systems, proving nature can exploit quantum weirdness outside frigid lab conditions. If microtubules perform similar tricks, the brain could be performing quantum operations that subtly entangle with spacetime itself, the most radical possibility. Orch-or implies consciousness might not be trapped in the present. If quantum states in our brains interact with the fundamental fabric of reality, then every thought could ripple across time's surface like a stone skipping on a pond. Meditation's timeless moments, psychedelics warp time perception, even creative inspiration's sudden flashes. These might be micro-instances of quantum consciousness brushing against deeper temporal layers. It's as if the mind isn't just observing time but participating in its weave, occasionally pulling threads from past or future into the tapestry of now. While mainstream neuroscience remains skeptical, Orch-or forces a profound question. If time is more fluid than we think, could consciousness be the hidden current that sometimes flows upstream? Penrose's theory may not offer blueprints for a time machine, but it hints that the ultimate vehicle for temporal travel has been inside us all along, waiting for us to learn how to steer. Dark matter is the universe's quiet giant, an invisible force shaping galaxies with its gravitational pull, yet refusing to interact with light or matter in any way we can directly detect. It makes up roughly 27% of the cosmos, outnumbering ordinary matter 5-1, and yet we still don't know what it's made of. But what if dark matter's secrets go deeper than just mass? What if its gravitational grip doesn't just bend space but time itself? Einstein showed us that gravity slows time. Clocks tick slower on Earth's surface than in orbit, and near a black hole, time grinds to a near halt. If dark matter truly is everywhere, woven through galaxies in vast, diffuse halos, its collective gravity could be warping time in subtle ways we haven't yet noticed. Picture a river flowing smoothly on the surface while invisible currents tug at its depths. Dark matter might be creating similar ripples in the fabric of time, too faint for our instruments to catch. Some theories even suggest that dark matter's distribution isn't uniform. It could clump into dense filaments or swirling vortices, creating localized pockets where time runs slightly faster or slower than the surrounding space. These distortions would be minuscule, maybe a few nanoseconds over centuries, but in a universe where precision matters, those tiny shifts could add up. The wildest possibility, dark matter might not just passively warp time, it could be entangled with it in ways that defy our current physics. Certain exotic dark matter candidates, like hypothetical particles called mirror matter, could interact with their own separate version of time, creating parallel timelines that occasionally brush against ours. Others, like sterile neutrinos, might fleetingly decay into ordinary particles, releasing energy that briefly warps spacetime like a pebble dropped into a pond. Even more radical is the idea that dark matter isn't just influencing time, it might be a relic of it. Some models propose dark matter as a shadow left behind by the early universe, a frozen echo of a time when the laws of physics were fundamentally different. The challenge is detection. Our most sensitive atomic clocks can measure time dilation caused by altitude differences as small as a foot, but dark matter's effects would be far subtler. Future experiments might look for anomalies in pulsar signals, cosmic lighthouses whose ticks are precise enough to reveal spacetime's hidden texture. Or perhaps gravitational wave detectors, already tuned to spacetime's ripples, could catch whispers of dark matter's temporal fingerprints. Until then, dark matter remains the universe's most tantalizing blind spot. It's everywhere, sculpting the cosmos, yet slipping through our fingers like smoke. And if it's secretly bending time, then every second we spend searching for it might be stretching or shrinking in ways we can't yet perceive. The irony is delicious. The very stuff we're trying to understand could be warping the clock we're using to measure it. We think of time as an unbroken line stretching from past to future. But what if that line has an endpoint, a moment before which nothing existed, not even time itself? The Big Bang isn't just the birth of our universe, it might be the ultimate edge of reality, a singularity where the laws of physics as we know them break down completely. Picture standing at the edge of a waterfall, peering into the mist where the river vanishes. That's the dilemma of time travel at the Big Bang. If time began there, can you even conceive of a before to travel back to? General relativity describes the Big Bang as a state of infinite density and temperature, where spacetime curves into a point so sharp it punctures the fabric of causality. In this view, asking what happened before the Big Bang is like asking what's north of the North Pole, a question that dissolves into meaninglessness under the weight of its own paradox. Yet some theories refuse to accept this boundary. Quantum gravity models like loop quantum cosmology suggest the singularity might be a bridge rather than a barrier. Imagine the Big Bang as a cosmic tunnel with another universe collapsing on the far side, its death giving birth to our own. Time wouldn't end, it would pivot like a pendulum swinging back through a hidden dimension. The wildest possibilities emerge from multiverse theories. If our universe is one bubble in an eternal foam of expanding cosmos, each with its own Big Bang, then crossing between them might be the closest thing to traveling before time. Think of it like diving under a wave in the ocean. You surface in a different swell, one that began rising long before yours. Certain string theory models even propose higher dimensional brains colliding like symbols, their impact sparking new universes while older ones linger in unseen dimensions. In these scenarios, time travel wouldn't mean rewinding our timeline but slipping sideways into another's dawn. yet the obstacles are as profound as the theories. Without a working theory of quantum gravity, we can't calculate how matter or energy would behave at the Planck epoch, the first fraction of a second after the Big Bang, where quantum and gravitational forces duel for dominance. The energy required to probe these conditions dwarfs anything our particle colliders can produce. It's like trying to reconstruct a symphony from the echo of a single note. Perhaps the most haunting implication is existential. If time truly had a beginning, then all our grand visions of time machines might be trapped in its wake, like fish swimming in a pond that has no shore. Or maybe the Big Bang is just one note in a deeper, older song one we'll learn to play only when we finally understand the instrument of spacetime itself. String theory paints a universe far stranger than the four dimensions we experience, one where reality is woven from tiny vibrating strings dancing through 10 or 11 dimensions. These hidden layers might hold the key to time travel, not by bending spacetime as we know it, but by slipping through folds in the cosmic fabric our senses can't perceive. Picture a spider crawling across a bedsheet to the spider. The sheet is its entire world until someone pinches two corners together, creating a shortcut. That's the essence of string theory's approach: time travel through geometry we can't see. At the heart of this idea are brains, short for membranes, theoretical objects that could exist in higher dimensions like pages in a book. Our entire universe might be a three-dimensional brain floating in a higher dimensional bulk. If that's true, two distant moments in time could be mere millimeters apart in a dimension we can't perceive. Imagine etching 1969 and 2042 on opposite sides of a piece of paper. To flatlanders living on the sheet, those dates are unreachable. But fold the paper and they touch. In string theory, certain configurations of brains could create similar folds, allowing particles, or perhaps even conscious observers, to hop across epochs as easily as stepping through a door. The most tantalizing version of this involves cosmic strings, infinitely thin filaments of energy left over from the Big Bang. In some string theory models, two such strings moving in parallel could warp spacetime so severely that looping around them would send you backward in time. It's like winding a clock by walking around its hands instead of turning them. These strings wouldn't just bend time, they'd knit it into pretzels, creating pathways where cause and effect twist into knots. The catch: cosmic strings would require energies a quadrillion times beyond what our particle colliders can produce, making them more mathematical specters than practical tools. Yet there's another possibility. If our brain universe occasionally collides with others in the bulk, those impacts might leave scars where time flows differently. Like a stone dropped into a pond, these collisions could send ripples through dimensions we don't perceive, creating temporary bridges between moments that seem separate. Some versions of the ekpyrotic universe theory, a rival to cosmic inflation, suggest our Big Bang was actually such a collision. If so, the aftermath might contain wrinkles where time's arrow wobbles, offering glimpses into before and after. The real magic lies in closed time-like curves, which string theory allows under specific mind-bending conditions. Certain configurations of wrapped strings and brains could create loops where time circles back on itself like a Möbius strip. Unlike wormholes, which threaten to collapse under their own gravity, these curves might be stabilized by the unseen dimensions themselves, as if the higher dimensional bulk acts as scaffolding, propping open timelines that would otherwise snap shut. The implications are dizzying. Civilizations advanced enough to map the bulk could treat time like subway lines, hopping on and off at will. Of course, string theory remains unproven. Its mathematics so complex that even its practitioners debate which of its countless solutions might describe our reality. But that's the allure. It doesn't just suggest time travel is possible. It implies the universe might be built with layers of time we've only begun to imagine. Every vibrating string, every folded brain, could be a thread in a tapestry where past and future are just directions waiting to be explored. Until we unlock those higher dimensions, they remain the ultimate frontier, not just of space, but of time itself. What if the past, present, and future aren't slipping through our fingers, but already out there, fixed in place like landmarks on a map? This is the radical vision of eternalism, the philosophy that time is an illusion, and every moment, from the Big Bang to the heat death of the universe, exists simultaneously in a static, unchanging structure called the block universe. Imagine reality as a vast cosmic film reel, where every frame, every second of history is equally real, permanently preserved. You're not watching the movie, you're living inside one frozen frame, mistaking your position for the only now that exists. Einstein's relativity hints at this mind-bending possibility. Just as space lets us move freely between cities, time might simply be another dimension we're traveling through, except our consciousness rides along one fixed path, creating the illusion of a flowing present. Think of it like hiking through a mountain range. The trail behind you, the past, and the path ahead, the future, are both just as real as the rock beneath your feet, the present. The difference, unlike space, we can't turn around or change direction, at least not yet. But if the block universe is real, time travel wouldn't mean rewriting history. It would be navigating to a different part of the timeline, like flipping to a new chapter in a book that's already written. This flips every intuition about free will on its head. If the future is already out there, are our choices illusions? Eternalists argue no, your decisions still shape your experience, just as a character in a novel makes choices within a story that's already printed. The block universe doesn't erase agency, it redefines it. Your life isn't a river flowing toward a predetermined sea, but a thread woven into a tapestry where every stitch exists at once. The eerie beauty of eternalism lies in its simplicity. No paradoxes, no bootstrap loops, just a universe where time travel is reduced to navigation. Want to visit ancient Rome? In the block model, it's still there, preserved in spacetime's amber. The challenge isn't bending the rules, but finding the exit ramp from your current frame. Some physicists speculate that wormholes or warp bubbles could act as elevators between floors of the block, linking distant moments like doors in a corridor. Others suggest consciousness itself might hold the key. If we could perceive higher dimensions, we might step outside time's corridor and see the whole reel at once. Yet eternalism raises haunting questions. If all moments exist forever, does that make death meaningless? Is suffering eternally playing somewhere in the block? The philosophy offers no comfort, only a stark reframing. You're always alive somewhere in space-time, just as you're always 5 years old or 80 or not yet born. It's a view that dissolves fear of the future and nostalgia for the past into something stranger, the quiet awe of a universe that doesn't move through time but simply is. Have you ever been absolutely certain something happened, only to discover the rest of the world remembers it differently? This eerie sensation lies at the heart of the Mandela Effect, where thousands of people share vivid but factually incorrect memories, like Nelson Mandela dying in prison during the 1980s, he didn't, or the Berenstain Bears being spelled Berenstein, they never were. While psychologists chalk it up to collective false memories, some theorists propose something far stranger. What if these discrepancies are actually fingerprints of timeline shifts? Tiny fractures in reality caused by accidental time travel or quantum fluctuations. Consider the sheer volume of people who swear they recall specific details that never existed. The Monopoly Man's monocle, Curious George's tale, or Darth Vader's line in The Empire strikes back. Countless individuals insist these were real, despite overwhelming evidence to the contrary. Skeptics argue our brains are wired to misremember, filling gaps with plausible details. But what if the truth is more unsettling? Some interpretations of quantum mechanics suggest that every decision spawns alternate realities, the many worlds hypothesis, and under rare conditions, these timelines might briefly intersect or overwrite one another. Imagine a cosmic glitch where fragments of a neighboring universe's history bleed into ours. leaving swaths of people clinging to memories from a version of events that no longer exists. Time travel theories add another layer. If someone altered a past event even subtly, the ripple effects could create inconsistencies in collective memory. Think of reality as a tapestry. Pull one thread, and the image distorts just enough to confuse those who knew the original pattern. In this scenario, Mandela Effect errors might be remnants of the unedited timeline, lingering like echoes in our minds. Physicists like Dr. Ron Mallett, who studies time loops, speculate that certain quantum states could allow information to leak between temporal layers, creating these paradoxical memories. The creepiest possibility: we might be living through these shifts constantly without realizing it. Every déjà vu, every "wait, that's not how I remember it," could be a flicker of timelines realigning. Some researchers even suggest CERN Large Hadron Collider, by probing fundamental particles, might inadvertently nudge the fabric of reality, creating microscopic fractures where alternate histories briefly surface. It's as if the universe is a vast hard drive, and sometimes, just sometimes, we catch glimpses of the deleted files. Whether the Mandela Effect is a quirk of neurology or evidence of something deeper, one thing's certain: it forces us to question how securely the past is anchored. If so many can be so wrong about so much, what else might we all be misremembering, or was it never that way at all? Quantum teleportation already sounds like science fiction, particles vanishing from one place and reappearing in another, their properties perfectly preserved across distances. But what if this phenomenon could do more than bridge space? What if it could bend time itself? At the heart of quantum teleportation lies entanglement, that eerie connection where two particles mirror each other's states instantly, no matter how far apart they are. Scientists have used this to teleport quantum information between particles separated by miles, even between Earth and satellites in orbit. The process doesn't move matter through space, it rebuilds an identical quantum state elsewhere, like faxing a document but burning the original in the process. Now imagine tweaking this mechanism to rebuild a particle state not just somewhere else but someone else. The math hints at tantalizing possibilities. Quantum equations are time-symmetric, meaning they work just as well backward as forward. In theory, if you could entangle a particle state with another particle, not just in a different location but at a different time, you might effectively teleport information into the past or future. Picture a quantum version of a time capsule. You prepare a particle in a specific state today, then use entanglement to project that state onto its partner particle yesterday. The result: information appears to have traveled backward in time without violating causality, because the original particle state is destroyed in the process. Experiments have already demonstrated teleportation in time, on microscopic scales, sending quantum data a few nanoseconds into the past using carefully timed measurements. But scaling this up to macroscopic objects, let alone humans, dives into uncharted territory. For starters, quantum teleportation requires perfect knowledge of a particle state, something Heisenberg's uncertainty principle makes impossible for all properties simultaneously. Then there's the no-cloning theorem, which forbids creating identical copies of quantum systems. Even if you could teleport a person's quantum data, you'd need to annihilate their original form, hardly a reassuring prospect. And the energy requirements: teleporting a single atom's worth of information currently demands a lab full of lasers and supercooled detectors. Doing the same for trillions of atoms in a human body would require harnessing the power of stars. Yet the most fascinating roadblock might be causality itself. If you could teleport information to the past, you risk creating paradoxes like sending a message that prevents your own experiment from happening. Some physicists propose quantum mechanics naturally avoids these contradictions through post-selection, where only self-consistent timelines survive. Others suggest backward time teleportation might be possible only in parallel universes, where changes ripple into alternate histories rather than our own. The wildest implication, quantum teleportation might already be happening naturally. If entangled particles exist in a state outside classical time, their instantaneous connection could be a form of temporal tunneling, whispers between moments we perceive as separate. Perhaps the universe has been time traveling all along, right under our noses, in the quiet dance of particles we're only beginning to understand. Until we crack the code, quantum teleportation remains a dazzling mirage, simultaneously the most promising and most perilous path to touching time itself. If time travel is possible, where are all the tourists from the future? This haunting question is a twist on the Fermi paradox, the eerie silence where we'd expect a cosmic cacophony. Just as physicist Enrico Fermi once wondered why we haven't found alien civilizations despite the universe's vast age, we might ask why our history isn't crawling with chrononauts. After all, if humanity ever unlocks time travel, wouldn't curiosity or even bureaucracy send someone back to document pivotal moments or just gawk at dinosaurs? One chilling explanation is that they're already here, hiding in plain sight. Advanced time travelers might possess technology indistinguishable from magic, blending seamlessly into our era while observing under strict non-interference protocols. Think of it like anthropologists studying an uncontacted tribe, silent, invisible, and careful not to disturb the timeline. Some even speculate that UFO sightings or historical miracles could be misinterpreted glimpses of temporal visitors. The 1896 airship mystery, where dozens reported a bizarre flying machine over California decades before planes existed, or Renaissance paintings depicting strange aerial objects, might these be artifacts of careless tourists from tomorrow? But secrecy isn't the only possibility. Perhaps no one visits because humanity never gets the chance to build time machines. Civilizations capable of temporal engineering might be extraordinarily rare, snuffed out by wars, environmental collapse, or cosmic disasters before cracking the code. Or maybe time travel is possible only forward, not backward, leaving our descendants as stranded in their era as we are in ours. The grim implication. Every silent year that passes without visitors could be a countdown to our extinction. Then there's the uncomfortable idea that we're simply not interesting. Future historians might regard our era the way we view the Dark Ages, a gap in the records best skipped over. Or temporal tourism could be tightly regulated, with our century marked off limits to prevent contamination of pivotal events. Imagine a galactic heritage law preserving the 21st century as a sort of historical nature reserve, where interference risks altering the fragile ecosystem of progress. The darkest twist, time travel might be possible, but the universe self-corrects. Any attempt to visit the past could trigger catastrophic feedback loops, Hawking's chronology protection in action, erasing the intervention before it leaves a trace. Like trying to carve your name in water, the timeline heals instantly behind every would-be time traveler, leaving no evidence they were ever here. Or perhaps the answer is simpler: we're looking in the wrong places. Time tourists wouldn't flock to crowded cities or famous battles. They'd seek untouched corners where their presence wouldn't ripple through history. A quiet forest, a desert at midnight, the depths of the ocean. Maybe the proof is all around us, hidden not in grand anomalies, but in the quiet cracks of reality we've learned to ignore. Until we know what to search for, the silence remains a riddle hanging over every theory, every equation, every dream of touching time. What if time isn't a fundamental force of nature, but just a line of code in an unfathomably advanced simulation? The simulation argument, popularized by philosopher Nick Bostrom, suggests our entire reality might be an artificial construct, a digital universe running on some extraterrestrial supercomputer. In this scenario, time travel wouldn't require bending spacetime or opening wormholes. It would be as simple as accessing the simulation source code and editing the clock speed, rewinding events like scrolling through a video timeline. Think of it like debugging a virtual world, The programmers could pause execution, roll back to a previous save state, or fast forward to see how variables play out. This idea gains eerie traction when you consider glitches in our own reality déjà vu, the Mandela Effect, or quantum behaviors that seem to defy classical physics. Could these be artifacts of rendering errors or patches applied to the simulation? Even more unsettling, if the simulators wanted to observe alternate histories, they might spin up parallel instances where different choices play out, effectively creating branching timelines without the need for multiverses. Time travel here isn't a physical journey, it's a permission setting, but the simulation hypothesis flips traditional time travel paradoxes on their head. If a simulated entity became aware of its nature and manipulated the system to revisit the past, would that constitute free will or just scripted behavior? And what's stopping the simulators from hitting Ctrl+Z on our entire universe? Some theorists propose that a sufficiently advanced simulation would include failsafes to prevent such tampering, like Hawking's chronology protection, but coded into reality's firmware. Others speculate that glitches might be intentional Easter eggs, left behind to nudge us toward questioning our existence. The most tantalizing clue could lie in quantum mechanics. The discrete, probabilistic nature of particles at microscopic scales mirrors how computers handle resource-intensive calculations, rendering detail only when observed. Even the speed of light might function as a processing limit, preventing the simulation from overloading. If we ever discover fundamental pixelation in spacetime or energy at the Planck scale, it could be the smoking gun that we're living in someone else's physics engine. Of course, the simulation argument remains untestable by conventional science, but its implications for time are staggering. If reality is code, then the past and future might not be lost or unformed, just temporarily unloaded from memory. The simulators could recompile the universe with different initial conditions, making big bangs as easily as hitting reset. For now, it's a thought experiment that blurs the line between metaphysics and computer science. But it forces us to wonder, if time travel is possible, maybe we're not the travelers, we're the variables being manipulated. The grandfather paradox isn't just a brain teaser, it's a ticking time bomb at the heart of every time travel theory. Picture this: you hop back to 1925 and prevent your grandfather from meeting your grandmother. Without their union, you'd never be born, which means you couldn't have traveled back to stop them. The paradox unravels causality like a loose thread, leaving physicists scrambling to stitch reality back together. But what if the solution isn't avoiding the paradox, but redefining it entirely? Modern physics offers two escape routes. First, the many worlds interpretation paints a far messier but paradox-free picture. Every decision forks the universe into parallel timelines, meaning your meddling doesn't erase your own history, it spawns a new one where you never existed. Think of it like stepping off a train onto a different track. The original timeline chugs onward, untouched, while you carve a fresh path where your grandparents' love story ends before it begins. Quantum experiments add weight to this idea. Particles seemingly choose multiple outcomes simultaneously, as if testing alternate realities. If consciousness follows suit, time travel might be less about changing history and more about switching channels. Then there's the elegant brutality of self-consistency. Russian physicist Igor Novikov argued the universe has a built-in antivirus for paradoxes. Any time-traveling shenanigans must align perfectly with established events. Try to shoot your grandfather, the gun jams, leave a warning letter, it gets lost in a drawer until after the disaster it predicted. Reality becomes a cosmic Rube Goldberg machine, where every intervention was always part of history. This isn't just philosophy, the math checks out. Kip Thorne's wormhole calculations show quantum probabilities skew wildly near closed time-like curves, nudging events toward consistency like a croupier rigging a roulette wheel. But the darkest twist lies in between these theories. What if both mechanisms apply? Imagine a universe where minor changes spawn parallel worlds, but cataclysmic paradoxes trigger self-correction. You might alter small details, your grandfather's job, his hometown, without erasing yourself, but attempting genocide-level interference slams the brakes. It's as if spacetime has fail-safes, split for a scratch but fuse shut before an amputation. The grandfather paradox endures because it forces us to confront the unthinkable. That time might not be a story we can edit, but a labyrinth where every turn was always part of the design. Whether through infinite branches or unyielding loops, the universe seems determined to remind us some threads can't be pulled without unraveling the whole sweater. And that may be the most humbling lesson of all. Time travel doesn't just challenge physics, it forces us to ask whether we're authors of our fate or merely scribes. From Einstein's relativistic time dilation to the flickering possibilities of quantum entanglement, we've journeyed through 30 distinct theories that each reimagine how time travel could lurk within the fabric of reality. Some, like wormholes and warp drives, tease us with cosmic shortcuts, tangible doors waiting for humanity to forge the right key. Others, like the holographic principle or quantum retrocausality, dissolve time entirely, suggesting it's nothing more than an elaborate illusion, a stage curtain we've mistaken for the show itself. And then there are the wild cards, the consciousness-driven voyages of Orch or theory, or the glitch in the matrix logic of the simulation hypothesis that turn time travel from a physics puzzle into a philosophical riddle. Each lens offers something vital, not just a blueprint for bending time, but a revelation about how little we truly understand it. The Tipler cylinder reminds us that relativity's equations might already permit time loops if only we could assemble the impossible materials. The Mandela Effect whispers that our memories might be fragile palimpsests rewritten by forces we can't perceive. Even the chilling silence of the Fermi time paradox forces a humbling question. Are we alone in time because we're doomed, or because the universe guards its secrets too well? What unites these theories isn't just their audacity, but their insistence that time is stranger than our linear minds can grasp. Whether it's the fractal branching of the many worlds interpretation or the frozen eternity of the block universe, they all agree on one thing: the clock in your kitchen is lying to you. Time isn't simple, it's not uniform, and if even a fraction of these ideas hold weight, it might not be unbreakable. So here's the question that lingers after the equations fade. Which of these visions feels most like truth to you? Is time a river we'll one day learn to sail upstream, or a locked door waiting for a quantum key? Or something else entirely, a dimension we're only beginning to decode? Drop your thoughts below and let's keep the conversation twisting through time. After all, the next great theory might not come from a lab, but from a comment section like this one.